Thanks, Michelle, and thanks also to all the organizers and to the Chalmers Institute for this wonderful setting and opportunity. Alistair said yesterday at the start that that they're interested in cross-fertilizing themes and so on, and this year the Chalmers Institute is running these two themes, one on the present theme on real analysis, whatever real means, and later on, or they already started, the other theme on big data. And the talk today is going to be something that attempts to straddle across these two themes, to take concentration, which is one of the central tools in the theme on real analysis and applications, and see how it applies to this area in machine learning, which is an application to big data, in particular to techniques dealing with support vector machines and kernels. So I'll start by reviewing the Johnson-Lindenstrauss lemma, which is kind of the mother of all concentration results, very classical and beautiful, and then show that this is, or attempt to make the case that this is making a strong comeback today, in the sense that there is a huge interest in applications of these kinds of ideas in the area of machine learning and big data. So the classical Johnson-Lindenstrauss lemma is that if you have n points in high dimensional space, so the capital D there, which will stand for dimension, is intentionally put as in large case, because we are always going to think of this is extremely high dimension. So this is the thing of interest in machine learning applications. So you have n points in extremely high dimensional space, and what the Johnson-Lindenstrauss lemma allows us to do is to project them into a much smaller dimension, which is little k, and the projection has the property that all interpair distances are preserved approximately up to any desired accuracy, 1 plus minus epsilon. And the interesting thing is the projected dimension is independent of the original dimension and only depends on the number of points, and it's logarithmic in the number of points. And this is known to be essentially tight by the results of Alon. So the original proof was to take a random linear map, which is an orthogonal projection onto k-dimensional subspace, and then use measure concentration on the sphere, the famous Dvoretsky's theorem. But by now today, there are many more, there's much simpler proofs, elementary proofs, and after a number of people wrote papers on this, and there's a very nice streamlined presentation that we have today.
Yeah, just a small comment. You don't need Dvoretsky for this. V's concentration is more than enough for this.
Yeah, so that probably reflects why people, that's.
No, you don't need anything.
But this is how they did it originally, I think. So, as I said, the Johnson-Lindenstrauss lemma is making a big comeback today in the area of big data, and has found lots of applications in many different areas, with proximity problems, online data streaming problems, and in a slightly related different area, compressed sensing. So there are a number of different areas currently where these kinds of ideas of random projections onto low dimensions are playing a very central role today. And today, I'm only going to address the applications in machine learning and to one particular sub-area within it, which is to the use of kernel methods and support vector machines. So just to recall the way the Johnson-Lindenstrauss lemma is proved, well, there's what you do is you take a random linear mapping with these parameters, and that random linear mapping has these properties, and this mapping is universal, and the projected dimension depends only on epsilon and delta, not on the original dimension. And this mapping is this mapping is particularly simple, so it's just multiplication with a suitable random matrix M, and the matrix M has dimension k by d, and the entries are Gaussian IID normal 0, 1. So it's can't possibly be a simpler mapping than this, and this one has the properties that are stated in the statement of the Johnson-Lindenstrauss lemma. And the distributional version, so this is stated by saying that, well, if you take a fixed point, then the 2 norm of the fixed point is preserved up to epsilon by this random linear mapping. And this version, of course, implies the other one by taking suitable choice of parameters. So it's in some another way, it's a classic application of the probabilistic method. Okay, so so that's the basic simple constructions. I'm going to talk about many variations of this construction that are now needed for applications to big data. But before that, let me do a short primer on support vector machines and classification by support vector machines. So in machine learning problems, data is represented by typically, quite often, as high dimensional vectors. And although the ambient dimension can be extremely high, these vectors are often extremely sparse. So here are some examples. So if documents are represented as bags of words, then the vector corresponding to a document is the ith coordinate is the number of occurrences of word I in the document. If it's user ratings, then it's the rating given by to a movie I by a particular user on Netflix. So in all these applications, the ambient dimension is extremely high, but the number of non-zero entries are very small. So this is something to keep in mind as we go along. The ambient dimension is high, but there are only a very small number of non-zero coordinates. So the classification problem then is that you're given, so this is a classification supervised learning problem in machine learning. So what you have are n training examples, xi, yi. So the xi are the data points represented as these vectors, these sparse vectors in very high dimension, and the yi's are labels, plus minus 1, say, binary classification. And the classifier is just a function that maps these vectors to -1, +1 using, and it's constructed using the given data as a training set. And the goal is to construct a function which has nice properties, in the sense that if you want to classify a new point, then the probability of misclassification should be minimized. So the risk, the risk of misclassification should be minimized. So a very classical approach to this is to use linear classifiers. So the idea here is to take a hyperplane, which is specified by this vector w, and use the sign of this linear function as the classifier. So this is perhaps the simplest approach, and this is a very common approach still today. Now the problem is there can be many different linear classifiers. So here's a simple example with a data set where there are many different classifiers, linear classifiers, which separate these two. So amongst this large class of possible classifiers here, which is the one should pick? So the support vector machine methodology is to pick the linear classifier, the hyperplane, which has the largest margin. And margin is as depicted in this figure. So here's the line that separates these two data points, and the margin is the distance between the closest point in one set to the line plus the closest point in the other set to the line. So sum of those two things, and that's the margin of the classifier.
I'm sorry, I don't understand the rules of the game. Why you're assuming that the black and white points belong to two sets which are separated?
Yeah, so for simplicity, let's assume that this is indeed the case, that there are really two kinds of the original data comes from a distribution which has two very widely separated classes. So in a typical application, I mean, you have a cancer patient and a healthy patient, and their gene microarray measurements, for example, will be very different corresponding to this.
Very different doesn't mean that they can be separated.
Well, they are not in general, but just to make it simple, I showed them as really cleanly separated like this. Of course, in reality, it may not be cleanly separated, and that's another issue.
My second question was, you said that the sample is from an unknown distribution. Are you assuming some... If you assume nothing about the distribution, then you can...
Yeah, so if you want to prove a statistical result, then you need some assumptions on the kind of distribution that there are really two separated classes, and you have enough examples from
So
both.
should we think uniform random?
No, it's not uniform random, but you could think of two very separated Gaussians, for example, with very widely separated means. If you want to think of the statistical aspect, so you have two distributions which have they are widely separated in some way, and the classifier will try to find without knowing what the distribution is. So the approach is to find this linear classifier which maximizes the distance like this, the margin between the two sets of points. So as Ehud pointed out, in actual real practice, it may not be so cleanly separable. Now there are extensions of this method to apply to that kind of situation where the data may not be cleanly separated, but let's not get into that. Let's stick to this is the separable case, so we'll stick only to the separable case. So the formulation as an optimization problem becomes this. So the goal of maximizing the margin becomes this optimization problem. It's minimize the two norm of this vector W subject to these constraints, which simply say that the two classes are separated correctly. And this is the famous SVM formulation. So another way of formulating the same thing, a equivalent way of writing this is to think of it as finding the distance between the convex hulls of two sets of points. So you have two classes A and B, and the support vector machine is actually finding the distance between these two convex polyhedra. This is an equivalent way of looking at the support vector machine formulation. And we'll kind of exploit this later. Now, the standard machinery in optimization, you apply the Lagrangian duality, you get the dual formulation in terms of these variables alpha. So this is an equivalent, just the dual of the formulation that I displayed on the previous slide. And the optimization problem here, this is a quadratic optimization problem. This also gives you information about about the structure of the optimal solution W. It is a linear combination of the input points. So this is the reason for calling it support vector machine. So they are exactly these points that correspond to non-zero coordinates in this dual formulation alpha. And being non-zero means, with the complementary slackness and so on, those constraints are satisfied with equality. So this is the reason why these things are called support vector machines. Now, another interesting thing to observe here is that the separating hyperplane has a nice explicit description, and this description only involves the dot products of the original data points. So it's given explicitly by this formula, and the only thing that you need are xi transpose x. So just the dot product between the training set vectors and the new point that you want to classify. So this is often written as a function k, and this k is what is in this area called the kernel. So there's another good point to keep in mind, that often in these support vector machine methods, what you really need are only these dot products. Now, another nice feature of support vector machines is, even though the description as we saw before involved a linear classifier, it can be used also as a nonlinear classifier. And this happens when you take the original points and project it into a very high dimension. So here's an example, toy example. So the green and the red points are clearly separable, but the separator is not a linear. It's not linear. It's a nonlinear surface. But if you project these points into some other space, into a much higher dimensional space, then in the higher dimensional space, the classifier can be constructed as a linear classifier. So there's a specific example here in 2 dimensions. So if you take this example in 2 dimensions, and then this embedding into 3 dimensionals with xi squared, x2 squared in these 2 coordinates, and x1, x2 in the third coordinate, this project this embedding into a higher dimension has the property that now there is a linear classifier in this three-dimensional space separating these 2 points. So this is another interesting thing, that you can take something which has only a nonlinear classifier in the original, nonlinear separated in the original space, and then by embedding it into a higher dimension, you can actually achieve this linear separation. So in the machine learning literature, this is called the Kernel Trick, because again, in order to do this in the higher dimension, you only need the dot products of the embedding. You only need phi xi transpose phi xj, and so you only need these dot products, and so the embedding is often only represented implicitly via such a matrix K. And there's a condition on when a matrix K defines such an embedding. The condition is that this matrix has to be positive semi-definite. So here are some examples that are used a lot in practice: linear kernel, quadratic kernel, polynomial kernel. So the basic message here is that often in these machine learning applications, data is not presented, need not be presented explicitly, but only via similarity kernel. So you only get this matrix K that measures in some way how these 2 objects are similar, and this is a positive semi-definite matrix, and this embedding that you need for these methods is only implicit. And in some cases, it may be very high dimensional or even infinite. So here is the radial basis kernel, which is very popularly used in applications. This corresponds, by the theorem, you know that there is an embedding corresponding to this matrix, but this embedding is actually infinite dimensional. So you do have cases where the similarity kernel is going to be not only high dimensional, but can even be infinite dimensional. So this is another thing that these methods have to deal with. So we are going to come back to this at some point. So in machine learning things, one of the 2 things, it's important to be able to work only with kernel representations, but these kernel representations may correspond to high or even infinite dimensional embeddings. So now if you take, we are interested in fast algorithms to solve these problems. They have to scale to very large dimensions. So in typical applications in Google these days, they consider data which is million dimensional and billions of data points and so on. So it has to scale to those kinds of numbers. And so the running time of these solvers is really crucial. So there are many methods today available for solving this optimization problem for the support vector machines, and here are the running times of some of the most popular ones. And you see there is a dependence on both n and d in some cases, but in other cases there's a dependence only on d and not on n. So the last mentioned method is a stochastic method and has kind of some interesting properties that it doesn't really depend on n, it only depends on the dimension. But all of them do depend on dimension, so the dimension is a very important parameter in these problems. And so when you have these very high dimensional points, this is an issue. So how do you cope with these very high dimensions when the running time, it enters into the running time in this way? So here is a direct first use of the Johnson-Lindenstrauss idea. If the dimension is an important thing, one can so this is the first take, so the most direct take, that you take the original data points and you project them into a very low dimension, preserving the margin. So since the Johnson-Lindenstrauss lemma preserves distances between points, it's going to preserve the margin of the classifier up to 1 minus epsilon factor. So the first simple direct idea is project the original data points into a low dimension and then apply the SVM methods. And then the running time, the dimension that appears in the running time will be the smaller dimension. There's so this is pretty immediate, but there is one needs to take some care here, because you have to take into account the computation time now to do the projection. And if you do it naively, this is quite expensive. So it's going to be order k times d per data point. And so here the big dimension enters the picture here. So just doing the projection naively is going to be expensive. And now let's remember that the input data is high dimensional but is often sparse. So the number of non-zero coordinates can be much smaller than the total number of dimensions. So the question is, can we exploit this in order to do the projection much faster than doing this in the most straightforward, direct fashion? So there's been a lot of work in that direction in how to compute this projection faster, still retaining all the nice properties of the Johnson-Lindenstrauss lemma. A number of different people got faster methods. And today, I guess the best, the state of the art is the construction by Kane and Nelson. And they achieve projection into dimension k, which is optimal, 1 over epsilon squared log 1 over delta. And the important thing is that the sparsity, they have a very sparse matrix. So now the matrix that you construct the projection with is not the original matrix where you had IID Gaussian entries. The idea is to make the matrix much sparser so you can compute the projection faster. And all these methods were different ways of getting sparser matrices, and the construction by K. Nelson is the best one in this direction today. And their construction has the property that each column has at most S given by 1 over epsilon times log 1 over delta non-zero entries. And
why is that better than the Clarkson-Woodruff thing? Does this in sparsity time?
Better than the Woodruff.
Woodruff and Clarkson have the sparsity time projection?
I think it's comparable. It's about the same. Their construction has similar properties too. But I think this was earlier.
Okay. I mean, this is early. I thought Clarkson-Woodruff would have been stronger here. But
No, I don't think I think this is, the parameters are roughly the same. So this has the projection time is going to be S, the sparsity times the number of non-zero entries in the matrix. So you get the fast computing of the projections.
What is the matrix? I don't understand. Is the projection of there was no matrix before? No, there is a matrix. Where is coming?
No, there was a matrix at the. So you remember the Johnson-Lindenstrauss projection is given by just multiplying the input x by a matrix M. And that matrix M,
This is a matrix
And
of
then a
projection.
map that gives the projection.
Okay.
and that matrix has just IID Gaussian entries. That was the original. And now the idea is just to make that matrix much sparser, still retaining all the properties. Now, K. Nelson have this construction, but this construction has, so it's not as nice in terms of, it's not independent. I mean, it's a more complicated construction. And it presents a challenge to this community because, well, the construction involves dependent random variables, so there's no independence anymore. And then if you want to get the concentration results, you need concentration results which are able to handle this dependence. So in the K. Nelson paper, they do a lot of elaborate calculations, explicit, elaborate, and massive calculations of higher moments in order to get the concentration results. But it would be nice to do this in a more principled fashion, I mean in a more uniform way which you can reuse later, because doing these explicit computations has to be redone every time you have to change the application a little bit. You have to redo the computation of higher moments all over again. So the question is there a way to prove concentration for these kinds of constructions in a unified fashion? So to adapt the concentration results when you have the kind of dependent variables you have in the K-Nelson construction. So one approach that seems hopeful is that in fact the dependence that you get in that construction has some kind of negative dependence property. So this was mentioned yesterday in one of the talks, a version of this. So this is a property called negative association. So it's a strong negative dependence condition. The condition is that if you take two non-decreasing functions, any arbitrary non-decreasing functions f and g of disjoint sets of these variables, then the correlation is negative. So the expectation of the product is less than the product of the expectations for non-decreasing functions and disjoint sets of variables. So the Kane-Nelson construction does have this property that the coordinates of the projected vector, as long as the vector has non-negative coordinates, so for the special case, they are negatively associated. And each coordinate is sub-Gaussian, so you do recover the original, the concentration results of the projection by exploiting this fact. But this only works for one of the constructions and for a case when the input point has non-negative coordinates. So it would be interesting to see if it works in general for the construction. Okay, so now I'd like to go to so this was the most direct application of Johnson-Lindenstrauss lemma. Now to a less direct application, which is when the data is only given in the form of similarity kernels. There is no associated there's no embedding. You don't have the embedding to work with, so you can't apply the projection directly. So what happens in this case? How can you approach this problem when the data is only given in this form of the similarity kernel and not with a explicit representation in high-dimensional space? So here there's an approach via what I call LP-type abstract optimization problems that is very useful. So the idea goes back to random sampling methods for linear programming. And just a very simple idea, you take a random sample of the constraints, you solve the LP on that random sample, keep the basis that determines the optimum, and now you look at the other constraints, and if some of the other constraints are violated, then you update the basis with respect to the violated constraint, and you continue until there are no violated constraints. So this is the basic simple idea behind Seidel's linear time algorithm for linear programming in small dimensions, which initiated all this work. So it turns out that the same ideas are applicable in a wider context, not just to the linear programming problem itself. So there are a bunch of other types of problems for which the same kind of idea, a random sampling idea, works. If you want to compute the smallest enclosing ball of a set of points, or various other ellipsoids or annulus. And in particular, to this problem that is of interest to us today in this context, the distance between two convex polyhedra. This is the SVM problem. It turns out that this falls into the same class of problems called the abstract LP type of problems. So what is common is that in all these problems, the optimum solution is determined by a small number of input objects. This is called the combinatorial dimension. The solution value is monotonic. It only increases or decreases if you add more objects. And there is a locality property that if the solution increases or decreases by adding more input objects, it already does so by adding those objects to the combinatorial dimension number of objects in the basis. So the abstract framework for LP-type problems involves a finite set H. You can think of it in the LP problem as the finite set of constraints, or in the SVM problem as the points with the labels. And then there is, to each subset of H, there is a value, there's a function W that assigns it a real value. And this function W has these two properties. It's monotonic, and it has a locality property. So if adding a point H to, if you have two sets F and G that have the same value, and adding a new point H to one of the sets increases the value, then it also increases the value for the other set. So this kind of very nice, simple setup. So this is all you need, the common abstraction from all these different examples. You just need this common abstraction. And then you have what is called, so to solve the optimization problem, you need two primitives. You need a violation test. Does the value of the objective function increase if you add a new point? And you need a basis update when you find such a violation and want to update the basis. So as long as you have this abstraction and you have these two primitives, then you have a common algorithm to solve all of these problems. This is the random sampling algorithm for LP-type problems. And the idea is very similar to the original random sampling idea of Seidel. So you start with a random subset H of the original set H of size delta. You start with a null basis and you update it to this set of points you added. And you compute the violators, And then you repeatedly choose a random subset of points from the remaining, you add it to this basis, you find the new violators, and you continue. So it's the same idea that you had in the original LP problem of Seidel, and you can more or less apply the same thing in this abstract framework. And the nice thing is that you can analyze the running time of this algorithm exactly, and this was done in the famous paper by Matuszek, Scherer, and Welzel, and the running time of the algorithm is n times 2 to the combinatorial dimension delta, square root of the combinatorial dimension delta. So when this delta is small, then this is a linear time algorithm. So coming back to the SVM, so you can take this algorithm and apply it to the SVM problem. And here, so here's where we use the fact that this is the SVM problem is a problem of this class. It's about separating two convex hyperplanes, and so the combinatorial dimension of this is d plus 2. So, and you do have violation and basis updates from the SVM machinery. You do have, you can implement these two for this problem. So applying this Matuszek, Scherer, Welzel algorithm to the SVM problem, so this is just repeating that in the context of SVM. You get an algorithm whose running time is going to be n, the number of points, to the 2 to the square root of the dimension. So now here is the second application of Johnson-Lindenstrauss lemma. So as long as you're willing to work in much smaller with an approximate solution, so you want a near optimal margin, then you can work. So the dimension appears there as in the exponential, it appears as 2 to the square root d. So by using the Johnson-Lindenstrauss lemma, you can go to a much smaller dimension now and still retain more or less the original margin. And the running time now becomes n to the 2 to the square root log n log log n, so it's little of n squared. And the important thing is that to do this, you don't need the explicit projection. So all of this can be done with the data represented only in the kernel form. So this is very important for SVM methods. So you get an algorithm for the SVM classification problem that only uses the kernel matrix and not the explicit projection. So this LP-type algorithm that I mentioned does not need the explicit representation in the high-dimensional space. Okay, so that was take 2 on using Johnson-Lindenstrauss with respect to for the classification problem. It gives you a running time which is little of n squared. The dimension has disappeared. So now we go back to the primal. So there are a number of reasons why this thing that we discussed just now, the dual formulation and using the kernel matrix K and so on, is a bit unsatisfactory today. One is that the number of support vectors can grow linearly in the training size. And you saw that earlier, one of the SVM methods that I showed you in the beginning had a running time that did not depend on n, just on the dimension. So that was something that that solved the problem in the original primal formulation. So there have been a number of recent advances in first-order methods for primal problems leading to extremely fast algorithms that scale to very large problems. So what you want to do really is again to go back to that primal formulation which uses the explicit representation in Euclidean space. So can you go back to that formulation? But the problem is you only have the kernel. So you have only the kernel matrix, you don't have the explicit representation, but somehow you'd like to use the explicit representation because you have all these fast methods when you have the explicit representation. And for some kernels, the embedding is actually is even infinite. So how can we do that? So again, the idea of random sampling. So we know that if you have this kind of kernel, this Mercer's theorem tells you that there is a representation like this. The problem is this representation phi can be in very high dimensional space or even infinite. So the simple random sampling idea is let's just take random samples from this infinite high or infinite representation. So let's work with a so let's approximate the kernel by something which is an empirical estimate of it formed by random sampling, and this random sampling will hopefully give us not only a good approximation to the kernel, but it also gives now an embedding that achieves this approximation. So that's the simple idea. Can we use random sampling to get an explicit representation which is a good approximation? And this is not going to be always possible, but it's possible at least for some kernels which have various kinds of symmetry properties which can be used to get, for example, it gives you, one example, if it's symmetry, the symmetry under with the symmetric group, then the Fourier basis gives you this kind of infinite expansion. So here's a simple example where it does work. So the famous Gaussian kernel, which is very commonly used in practice, this has the basis functions from the Fourier expansion given explicitly like this. It's e to the imaginary I times the inner product of z and x. And the kernel is just, so this is just the integral representation that I showed you before. It's the expectation of this dot product with these basis functions. So you have a very explicit representation for this particular kernel. So for these kinds of kernels, this random sampling idea can be used, and so this was proposed by Rahim and Recht in a paper in 2007. So their construction takes a random matrix Z, which is n times d with parameters n, the parameter n given by that estimate, 1 over epsilon squared d log 1 over delta. So that gives you an approximation to the RBF kernel in this form, and there is a concentration that the approximation is good with high probability. And this is just an application of the measure concentration for Lipschitz functions with the Gaussian measure. So this was proposed by Rahim and Recht. There's nice properties, and they showed that actually works quite well in practice as well. I don't know why they called it random kitchen sinks. No idea why they called it that. So now, so this is a nice thing. They showed it works, but the problem with this is again that computing these things. So this is again, you should again remind. So this construction should remind us again about the original Johnson-Lindenstrauss construction. This is a random matrix Z multiplying the original vector X. So this is exactly the same kind of construction, and we'll have the same problem, namely computing this matrix vector product is expensive. So can we do this faster? So this is a recent paper in the ICML this year by Lisa Alves and Smola, where they give a faster approximation of the kernel using a different matrix, which is again sparse, has some sparsity properties, and reduces the multiplication time to do this. And for a special case of this, they're able to prove a concentration using by adapting this Gaussian concentration of Lipschitz functions. And it applies to also other types of kernels, not just the Gaussian kernel I showed you, but kernels in the same family. Okay, so this is faster, but again one might, so the natural question one can ask is, can you use the kind of construction that you had in the Kane-Nelson construction and the that I showed before, which reduces the multiplication time to even more, to the minimum possible sparsity times the non-zero number of entries in the matrix? Can you get the same concentration results using the Kane-Nelson construction? So I believe this is the case, but again, this is where you need to prove those concentration in the presence of dependence. So there is a problem in trying to use to salvage those concentration results when you have the kind of dependence in the Kane-Nelson construction.
So probably what you want there, I mean, if you use the structure results Alex Gittins has and combines it with the Clarkson-Woodruff construction, the Kane-Nelson is a very complicated construction.
Yeah.
And don't look at the Clarkson-Woodruff, look at the extension Zhang-Meng has, where it just boils down to matrix multiplication, which is even simpler analysis.
Okay.
The construction's the same. So the Clarkson-Woodruff is a much simpler construction. If you combine that with the structure results Alex Gittins has, if I
Okay.
establish the conjecture in the precise form, the answer is definitely you can do it.
Okay.
But you don't have all those combinatorial dependencies.
Okay. Thanks. Okay, so then you already solved one of the problems I put up there.
I
Yeah, so to conclude, the Johnson-Lindenstrauss and other related methods that Woodruff and Clarkson-Woodruff and other types of methods, these have lots of applications in the machine learning, SVM and kernel methods. And so these constructions and concentration results should have even further impact on applications in these areas. So what I showed today was that there are three different ways you can do it. One is when you have the explicit embedding, then you can do a direct projection, use faster constructions of the projection. The second is when you only have the kernel and you want to do it implicitly, then you can use the LP-type methods to just get, you use the Johnson-Lindenstrauss lemma only to get the bound on the margin, but you don't actually do the projection. You use it in the LP-type framework. And the third is when you have the kernel and you want to approximate it in using random sampling. And this is possible only for a few types of kernels today. Maybe you can extend it to a larger class of kernels that has more applications in practice. And here there are many open problems in using concentration methods as well as fast construction and trying to combine them to get the best of both worlds. Thanks.
Any questions, remarks?
Do they use polynomial threshold functions for these machine learning contexts instead of linear classifiers?
Polynomial threshold functions?
That's like classifying using, say, so you classify using degree 1 polynomial, right? Using a linear function. So do they use ever?
I mean,
the kernel with the linear classifier.
Oh, I see.
the polynomial kernels, for example, is
I see. Thank you.
They don't use the parameter.
So the error that you want after the projection or when you approximate the kernel, doesn't it have to depend on the number of samples or at least number of support vectors in order for the thing to make sense afterwards? You're assuming that the error is just epsilon, but epsilon should be smaller as the number of samples increases because you kind of have an accumulated error there, right?
I mean, the epsilon, so that, I mean, the kind of error you're thinking about is some statistical error with a large number of, which should go to zero as you have more data points and so on. But the epsilon here was have to do more with the...
Yeah, I know, but still after you project, when you take the scatter product, this epsilon accumulates many times, right?
Not really. I mean, so in this construction, there was no accumulation of the epsilon. I mean, you do the projection of all the points, and the result, because the Johnson-Lindenstrauss it preserves the interpair distances of all pairs. You have there's one epsilon. I mean, the margin is preserved to 1 minus epsilon. That's it. I mean, there's no accumulation of the epsilons.
Well, but you don't take the scatter product with just 1 point.
No,
you take the sum
yes,
with.
yes, but the
so-
same 1 minus epsilon holds for all of them at once, without the accumulation of epsilon.
Questions? So if not, just send this again.